Parts 1 and 2 covered the trailers that move the majority of freight on the planet, and then the ones built for extreme loads and extreme dimensions. If you haven't seen those, the links are above. The comments on Part 2 told me I wasn't done. 2 separate people mentioned the walking floor in the first 9 hours. Someone paired it with the tilt deck and 3 other trailers I had already covered, which told me something. That viewer sees all of these as peers, and if I covered the others and skipped those, the gap was visible. So this is Part 3. And if Parts 1 and 2 had a theme, it was shape, what the trailer looks like, and what that shape allows it to carry. Part 3 is different. The trailers in this video are defined not by their shape, but by how they move, how they load, and how they unload. The mechanism is the point. Let's get into it. The walking floor. Every bulk trailer covered in this series so far unloads the same way. It tilts, or it opens a gate, or it blows air through the load. Something changes the orientation of the cargo, and gravity or pressure does the rest. The walking floor does none of that. It unloads while sitting perfectly flat and perfectly level, and it does it using one of the most elegant mechanical systems in freight. The floor of a walking floor trailer is made of interlocking aluminum slats running the full length of the trailer, typically 48 to 53 feet, or 14.6 to 16 meters, roughly the length of a telephone pole in the US, or the width of a 5-story building in Europe. Those slats are divided into 3 groups. The hydraulic system moves all 3 groups forward together, then pulls them back 1 group at a time, forward together, back 1 at a time, forward together, back 1 at a time. Here's why that works. When all 3 groups move forward simultaneously, friction between the slats and the cargo is equal across the whole floor, and the load moves with them toward the rear doors. When one group pulls back, the other 2 groups are still, and the friction from those 2 stationary groups holds the load in place, while the single moving group slides back beneath it. The load does not move backward, it stays. Then the next group slides back, then the third. Then all 3 go forward again, and the load advances another increment toward the doors. The result is continuous, controlled unloading of bulk material without any part of the trailer ever leaving the ground. No hydraulic lift, no tipping, no compressed air, just a floor that walks the cargo out the back at a controlled rate the operator manages from a simple control panel. What this means in practice is enormous. A walking floor can unload on surfaces where a tipping trailer cannot operate. Inside a building with a low ceiling, on a soft surface that cannot support the tilted weight of an end dump, on a sloped surface where raising a body would create a dangerous lean. Wood chips, municipal solid waste, shredded paper, biomass fuel, grain, sand, gravel, anything that flows or slides can be unloaded on a walking floor wherever the truck can physically park. Waste management facilities use them extensively because garbage compactors at transfer stations need a controlled feed rate, not a sudden avalanche from an end dump. Paper mills use them for wood chip delivery. Power plants use them for biomass fuel. Anywhere that bulk material needs to move out of a trailer in a controlled, measured way rather than all at once, the walking floor is the answer. The tilt deck. The flatbed loads heavy equipment by driving it on from the rear over a ramp or lifting it on from above with a crane. Both methods work. Both have limitations. The ramp takes time to set up and requires the right approach angle. The crane requires lifting equipment at the loading site, which is not always available. The tilt deck eliminates both problems by making the trailer itself the ramp. A tilt deck trailer, also called a tilt bed or rollback, has a deck hinged at or near the rear axle. A hydraulic cylinder raises the front of the deck, tilting the entire platform down toward the ground at the rear. The rear edge of the tilted deck touches or nearly touches the ground, creating a shallow loading angle across the full length of the trailer. Equipment drives up that angle under its own power. When the load is positioned correctly, the cylinder lowers the deck back to level, and the equipment is sitting flat on the trailer ready to be secured. A standard tilt deck runs 20 to 30 feet long, 6 to 9 meters, about the length of 2 parallel parking spaces end to end in either system. The tilt angle brings the rear of the deck to within a few inches of the ground, typically 4 to 6 inches or 10 to 15 centimeters, low enough for almost any wheeled or tracked equipment to board without high centering on a steep ramp angle. The industries that depend on tilt decks are the ones that move equipment constantly between job sites. Landscaping companies moving zero-turn mowers and skid steers. Equipment rental operations delivering and recovering machines daily. Towing companies recovering disabled vehicles. Small construction contractors moving a mini excavator from one residential job to the next. The tilt deck sits at the intersection of heavy equipment hauling and everyday logistics, not for the 40-ton excavator that needs a lowboy, but for the 6,000-pound, 2,700-kilogram machine that needs to be somewhere else by morning. The speed of loading is the defining advantage. A driver who knows the equipment can have a skid steer loaded, secured, and moving in under 5 minutes. No ramp to deploy and retrieve. No crane to wait for. The trailer does the work. The removable gooseneck. In Part 2, we covered the lowboy. The deck sitting 18 inches, 46 centimeters, off the ground, the double drop profile, the ability to carry tall and heavy loads that a step deck cannot handle. The removable gooseneck takes the lowboy one step further by solving the one limitation a fixed lowboy cannot overcome. On a fixed lowboy, equipment loads from the rear via a detachable tail section, or it gets craned on from above. For most machines, that works fine. But for very large, very heavy equipment, tracked machines weighing 50, 60, 70 tons or more, neither option is ideal. Driving on from the rear requires the machine to negotiate a ramp while already carrying enormous weight. Craning requires a crane capable of lifting that weight, which is not always on site. The removable gooseneck solves this by making the front of the trailer detach completely. The gooseneck, the curved front section that connects the trailer to the tractor, unlatches and the tractor drives forward, lowering the front of the trailer deck to the ground. The entire deck becomes a ground-level ramp. Equipment drives straight on from the front, fully under its own power, on a surface that is essentially flat. When the machine is positioned, the tractor backs under the gooseneck, it reattaches, and the front of the deck rises back to its working height. A loaded removable gooseneck trailer handles 50 to 150 tons depending on axle configuration, 110,000 to 330,000 pounds, roughly the weight of 7 to 22 fully loaded semi-trucks in the US, or 35 to 100 average European family cars stacked on a single platform. Large mining equipment, industrial rollers, massive generators, military armor, any tracked or wheeled machine too heavy to crane and too large to ramp conveniently, the removable gooseneck is the loading method that makes the move possible without specialized lifting equipment at the origin. The straddle trailer. This one came from a commenter on part 2 who described it specifically in the context of fruit bins, large harvest containers used in orchards, and the description pointed directly at a problem most people have never thought about. How do you transport a container that is already sitting on the ground, full of product, without lifting it from above and without driving anything underneath it? The straddle trailer answers that question with a frame that drives over the top of the load rather than under it. A straddle trailer has a wide, tall frame, typically 10 to 14 feet wide, or 3 to 4.3 meters, that straddles whatever it is picking up. The trailer drives forward so the load sits between the frame rails. Hydraulic legs lower the frame onto the load at specific contact points, or in the case of containers with fork pockets, engage directly into the pockets, and lift it off the ground. The trailer then carries the load suspended within the frame rather than sitting on a deck. The critical advantage for produce is what the commenter pointed out directly. Lifting a full fruit bin from above with a forklift risks bruising the top layer of fruit at the contact point. Lifting from below with standard forks risks the same at the base. The straddle trailer distributes the load at the sides of the container, at points specifically designed for that contact, and the fruit in between never experiences a concentrated load point. Across thousands of bins across a harvest season, that difference in bruising rate has direct economic value. Beyond produce, straddle trailers appear in precast concrete operations, moving large panels and beams, in industrial settings, moving machinery too wide for conventional loading, and in port operations, moving specialized containers. The unifying principle is always the same. The load is too large, too fragile, or too awkwardly positioned for conventional pickup, and the only practical solution is a trailer that drives around it instead of trying to get underneath it. The stretch single drop. In part 1, we covered the step deck, a short upper deck at standard height, a lower main deck behind it, giving tall cargo 2 extra feet, about 60 centimeters, of legal clearance compared to a standard flatbed. In part 2, we covered the extendable flatbed, which solves the length problem for cargo too long for a standard 53-foot, 16-meter trailer. The stretch single drop is what happens when you need both solutions at the same time. A load that is tall enough to need the lower deck profile of a step deck and long enough to need an extendable rear section. Wind energy components drove a lot of the demand for this trailer. A nacelle, the housing that sits at the top of a wind turbine containing the generator and gearbox, can weigh 80 to 100 tons, or 176,000 to 220,000 pounds, roughly the weight of 11 to 14 fully loaded school buses in the US, or 55 to 65 average European cars, and can be 15 to 20 feet, 4.6 to 6 meters, tall at its highest point. It needs the lower deck to stay within legal height limits, and its length means the extendable rear section is necessary to support it properly. The stretch single drop extends from a standard 48 feet, 14.6 meters, to configurations reaching 63 feet, 19.2 meters, or more depending on the specific trailer model, roughly the length of 6 standard parking spaces, end-to-end in the US, or just over the length of a standard shipping container placed twice end-to-end in Europe. The combination of lower deck and extended length makes this one of the most versatile trailers for oversized industrial components. Transformer housings, generator stators, industrial pressure vessels, large HVAC units for commercial buildings, anything where height and length are both pushing against legal limits simultaneously, and a standard step deck or standard extendable flatbed handles one problem, but not both. The hydraulic detachable tail. The lowboy float covered in part 2 was the specialist solution for getting tracked machinery onto a trailer without adding deck thickness to the ride height. The hydraulic detachable tail is the specialist solution for the other end of the loading problem, getting that same machinery off again at the destination, on ground that may not be level, without a crane, and without a fixed ramp structure at the delivery site. Most lowboy trailers have a removable rear section called a tail that allows equipment to drive off the back. On a basic detachable tail, that section is physically removed by hand, pins pulled, tail lifted clear, equipment drives off. On a hydraulic detachable tail, the process is controlled entirely by the trailer's own hydraulic system. The tail section lowers on hydraulic cylinders to meet the ground at the rear of the trailer. If the ground is uneven, a slope, a soft shoulder, a job site that has not been graded, the hydraulic system compensates, adjusting the tail angle to create a smooth transition from the trailer deck to the ground surface. The equipment operator drives off in a controlled descent rather than dropping onto a fixed ramp angle that may or may not match the terrain. For machine weights of 40 tons, 88,000 pounds, and above, the difference between a controlled hydraulic descent and a fixed angle ramp is not a minor convenience. At those weights, a few degrees of unexpected angle change during drive-off transfers, enormous force through the machine's undercarriage and the trailer structure simultaneously. The hydraulic tail absorbs that variable. It is the reason large excavators and bulldozers can be delivered to unprepared job sites, raw land, ungraded construction sites, active mine access roads, without a perfectly flat, perfectly firm unloading surface waiting for them. The beam trailer. Everything covered so far carries its load on top of a deck or within a frame. The beam trailer does neither. It carries its load by suspending it between two separate trailer units, with nothing underneath the cargo at all. Two self-powered or tractor-pulled dolly units, one at each end of the load, connect directly to whatever is being carried. The cargo itself becomes the structural bridge between them. A steel beam, a concrete girder, a large pipe section, any object with sufficient structural rigidity can be transported this way, hanging between the two dollies with open air beneath its entire length. The practical advantage is height, because there is no trailer deck, no frame, no platform, nothing between the cargo and the ground except the clearance the dolly wheels provide. The cargo rides at the absolute minimum possible height. A concrete bridge girder that would ride at 14 feet, 4.3 meters, on a lowboy can ride at 10 feet, 3 meters, on a beam trailer. Well within legal limits without permits in most jurisdictions, simply because the deck thickness is 0. Bridge construction is the primary application. Girders that span highway overpasses, railway bridges, and river crossings can run 100 to 200 feet long, 30 to 60 meters, the length of a full American football field from goalpost to goalpost in the US, or the length of 2 Olympic swimming pools placed end to end in Europe. No single conventional trailer handles those dimensions. The beam trailer handles them by turning the girder itself into the trailer. Large precast concrete sections, long steel fabrications, industrial pipe for major infrastructure projects. Anything structurally rigid and dimensionally extreme can ride on a beam trailer as long as the attachment points on the cargo are engineered to take the load. That engineering happens before the trailer ever arrives. The low bed modular. The extendable multi-axle platform in Part 2 was the largest trailer in the series. The low bed modular is the system that scales beyond even that. Not a single trailer with extensions, but a completely modular approach to moving loads that have no defined upper limit in size or weight. The system is built from standardized self-propelled modular transporter units, called SPMTs, each a low, flat platform on hydraulic axles, typically 8 feet, 2.4 meters, wide, and 6 to 8 feet, 1.8 to 2.4 meters, long per module, about the footprint of a large dining table. Each module has its own axles, its own hydraulics, and connects to adjacent modules mechanically and hydraulically to form a single coordinated platform of any size the load requires. Modules connect side by side to make the platform wider. Modules connect end to end to make it longer. The configuration is determined entirely by the dimensions and weight distribution of what is being carried. A small SPMT configuration for a 200-ton load might use 16 modules. A large configuration for a 2,000-ton refinery column, that is 4.4 million pounds, or about the weight of 280 fully loaded semi-trucks in the US, or roughly 1,300 average European cars, all sitting on one platform, might use 100 modules or more, across a platform the size of a basketball court. Every axle steers independently under computer control. The entire platform can move forward, backward, sideways, diagonally, or rotate in place. A 2,000-ton load can be sidestepped 3 feet, 1 meter, to the left without moving forward or backward at all. The precision this creates on a tight job site, positioning a reactor vessel onto foundation anchor bolts with millimeter accuracy, is not achievable any other way. Nuclear power plants, offshore oil platforms, refinery construction, bridge deck replacement, any project where the object being moved is itself larger than most buildings, the SPMT system is what makes the move possible. 3 videos, 30-something trailers, and the comment section keeps finding gaps. The walking floor moves cargo without tilting. The tilt deck loads without a ramp. The removable gooseneck turns the trailer itself into the loading surface. The beam trailer carries a load by suspending it in open air. The SPMT moves a 2,000-ton reactor vessel sideways by the length of an arm. Every one of these exists because someone had a load that no existing trailer could handle, and rather than leave the freight on the ground, they built something new. The commenter who mentioned the walking floor, the one who listed 5 trailers I had missed in a single comment. They are the reason Part 3 exists. If there is a Part 4, and the comment section will decide that, tell me below what I still haven't covered. I read every one of them, clearly.